Hello geometry students. Today's lesson is called dilations. This is another type of transformation, but unlike the other transformations we've learned so far, when we do a dilation, it doesn't produce a shape that is the same size as the original. This one will be a different size. So we're going to start by graphing the square BLUE with these coordinates on the grid over here at the left. So I'll start with B at 1, 1. L is at 3, 1. U is at 3, 3. And E is at 1, 3. And so we've got this shape. It's a square. I'm going to connect these points to form the square. Try to do it nice and neat using my ruler. It's kind of a tiny square. Okay. Next, it says, on the graph above, dilate the square using a scale factor of 3. We've talked about scale factors earlier this year. A scale factor is a number you multiply by. The center of dilation is the origin. Label the corresponding vertices B prime, L prime, U prime, E prime, and record the coordinates of the vertices of B prime, L prime, U prime, E prime in the image column of the table. I'm going to actually start by multiplying the coordinates and then plot them. So everything is going to get multiplied by 3. Both the x's and the y's. So 1, 1 will become 3, 3. 3, 1 will become 9, 3. 3, 3 will become 9, 9. And 1, 3 will become 3, 9. So I'm going to start by plotting these points. So 3, 3 is my new B prime, and that is going to lie on the same point where my U for the original figure was. L prime is at 9, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. So this is L prime. U prime is at 9, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. U prime. And then 3, 9. 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Is E prime. So now I'm going to connect those points to form my new dilated shape, which is the same shape as the original but larger. 3 times as large. All right, so there's my new square. It says for step 3, write a transformation rule that describes this dilation. xy becomes 3x, 3y. Remember, when you put the number right in front of the variable, that indicates that you are multiplying them. So this means 3 times x and 3 times y. So it says measure the sides and the angles of the original and the dilated square. Record the measurements in the table below. Calculate the perimeters and the areas of the original and the dilated squares. Record those measurements in the table below. Okay, so the side lengths of the original figure. If you look here, it was 2 by 2 by 2 by 2, all 2s. So their side lengths are 2s. Now the dilated image has side lengths of 1, 2, 3, 4, 5, 6. Okay. The angles in degrees are 90 degrees for both shapes. We didn't change the angles when we dilated it, just the side lengths. And then the perimeter. Well, for the original figure, it had 4 sides. Each one was 2 units long, so 4 times 2 equals 8. The perimeter was 8. The dilated shape has 4 sides. Each one is 6 units long, so 6 times 4 is equal to 24. And then the areas. To get an area of a square, you just do the length times the width. So 2 times 2 gives us an area of 4 for the little one. And 6 times 6 gives us an area of 36 for the large one. Now we have to answer some questions about this data. How do the side lengths of the original and the dilated image compare? So the side lengths were multiplied times 3. 2 times 3 equals 6. Multiplied by 3. How do the angle measurements of the original and the dilated image compare? They're the same. And how do the perimeters of the original and the dilated squares compare? How do you get from 8 to 24? Well, that's times 3 as well. Multiplied by 3. How do the areas of the original and the dilated squares compare? Well, this is not times 3. 4 times 3 is not 12. It's times 9. And the significance of the number 9 is that it is the scale factor squared. So multiplied by 3 squared, which is 9. So the reason that you have to square the scale factor is because the length multiplied times 3 and the width multiplied times 3. So the dimensions of the area are square units, and it actually multiplied by the 3 twice. 3 times 3 is 12, times 3 again is 36. Okay, next. Graph the quadrilateral EAGL with coordinates given here on the grid at left. So let's start by plotting these. 8, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. There's the point E. A is at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. G is at 10, 10. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And L is at 8, 10. So let me connect these using my ruler. I kind of put my E in a spot that I'm going to draw right over it to make this bottom side of this quadrilateral. Okay, so there's the original. Now, it says on the graph above, dilate the square using, oh, it's not a square. This is a rectangle. My apologies. Using a scale factor of 1/2. We're multiplying by 1/2. Keep in mind, multiplying by 1/2 is the same thing as dividing by 2. The center of the dilation is the origin. Label the corresponding vertices E prime, A prime, G prime, L prime. Record the coordinates of the vertices of E prime, A prime, G prime, L prime in the image column of the table. I'm going to multiply first and then graph it. So each one of these numbers is going to get multiplied by 1/2, which is the same thing as dividing by 2. So 8 times 1/2 would be 4. And 4 times 1/2 would be 2. 10 times 1/2 would be 5. 4 times 1/2 is 2. 10 becomes 5. 10 becomes 5. 8 becomes 4. And 10 becomes 5. So these are the coordinates of my new dilated image. And now I'm going to plot them and label them on the graph. So 4, 2 is E prime. 5, 2 is A prime. 5, 5 is G prime. And 4, 5 is L prime. And I'm going to connect them to make my new dilated rectangle. And number 11 says write a transformation rule that describes the dilation. So this is 1/2 x and 1/2 y. We've multiplied both the x and the y times 1/2. Now we need to record the side lengths, the angle measurements, the perimeters, and the areas of both the original figure and the dilated figure in the table here. So the side lengths of the original, the bottom is 2 and the right is 1, 2, 3, 4, 5, 6. So it's 2 by 6. 2 and 6 are the side lengths. Now the dilated image has a bottom side of 1 and a right side of 3. So 1 and 3. The angles are all 90-degree angles in both shapes. So 90 and 90, that didn't change. The perimeter of the original is 2 plus 2, which is 4, plus 6 plus 6, 12, and 4 makes 16. And the perimeter of the little one, the dilated one, is 1 plus 1 is 2, 3 plus 3 is 6, so that's 8. 6 plus 2. Okay, then the areas. We multiply the length times the width. So 2 times 6 equals 12, and 1 times 3 is 3. So how do the side lengths of the original and the dilated image compare? Well, they were multiplied by 1/2. How do the angle measurements of the original and the dilated image compare? They are the same. How do the perimeters of the original and the dilated rectangles compare? Well, the perimeter is multiplied by 1/2 also. And how do the areas of the original and the dilated rectangles compare? This is not times 1/2. 1/2 of 12 is 6. This is times 1/4, which is 1/2 times 1/2, or 1/2 squared. It is multiplied by 1/2 squared, which is equal to 1/4. Okay, next, state whether the figure appears to have line symmetry. That means you could draw a line and it would look the same on both sides. Write yes or no. If so, draw all the lines of symmetry and state the number of lines of symmetry that the figure has. So on number 17, yes, I think you could draw a line of symmetry to split this thing in half on the left and the right side. I think it could go straight through this upper vertex and the midpoint of the opposite side, like so. And that would be a line of symmetry. Now the question is that all the lines that it could have? I don't think so, because this looks like a regular pentagon, which means all the sides and the angles are congruent. So if I turned it so that this was the top vertex and this was the bottom side, I could draw another line that goes through that vertex and the midpoint of this bottom side, like this. Or I could turn it so that this was the top vertex and this was the bottom side, and go through another line like this. And what about if I made this the top vertex and this the bottom side? I could draw another line of symmetry going here And if this was the top vertex and this was the bottom side, I could draw another line of symmetry going right here. So, how many lines is that? Well, it was one for each vertex. 1, 2, 3, 4, 5. So, state the number of lines of symmetry. 5 lines of symmetry. Okay, how about number 18? Does this figure have line symmetry? Yes, I believe it does. I could draw a line going midway between those eyes on the smiley face, and I believe that it only has one line of symmetry. Be like a bilateral symmetry going on here. Now what about number 19? Does this one have a line of symmetry? Well, if I go up and down, it does not look the same on both sides. If I go left and right, it does not look the same on both sides. If I were to go this way, it does not look the same on both sides. So, no, this one does not have line symmetry. That one actually has rotational symmetry. If I were to rotate it upside down, it would look the same around the center, but that's not what it was asking on this problem. That's what we're actually asking on the next one. State whether the figure has rotational symmetry. Right, yes or no? If so, identify the angle of rotation and state the number of times that it will coincide with the original shape after rotating 360 degrees. Okay, so I think this one does look like if I rotate it, it's going to look the same. So I'm going to say yes, it has rotational symmetry. Now I need to figure out the number of times it will coincide after rotating 360 degrees and the angle of rotation. I'm going to do the number of times that it will coincide first. I'm going to start at the top and count how many times I rotate it where it looks the same. So 1, 2, 3, 4, 5, 6, 7, 8. Gets me back to where I started. So I'm going to say 8 times. You count the jumps. And so I need to figure out the angle of rotation. So you take 360 and divide it by the number of jumps. So how many times does 8 go into 36? Let's see, that would be 4 times. No, 8 times 4 is 32. Well, 4 times 8 is 32. No, I apologize. Yes, 4 times 8 is 32. Subtract 6 minus 2 is 4. Bring down your 0. 8 goes into 45 times. 5 times 8 is 40 with a remainder of 0. So the degrees, the angle of rotation is 45 degrees. So you always start with 360 because 360 degrees are the number in the whole circle, and you divide it by the number of jumps that you would make when rotating, where it's going to land and look the same as it started. Okay? Now number 21. Does this shape have rotational symmetry? Well, yes, I can rotate it and make it look exactly the same, but only if I rotate it a full 360 degrees. So technically, if you have to rotate it all the way around a whole circle to make it look the same, every shape would do that. And the answer is no, it does not have rotational symmetry. Now let's look at number 22. Pretend like the number is not on the problem because somehow that shape jumped out of its correct spot. But if I were to put my finger down in the center of this flag looking shape and rotate it 180 degrees, so upside down, it's going to look exactly the same. And then if I rotate it again back to the way we started, it again looks the same. So it goes from the top to the bottom and then from the bottom to the top. So we say yes, it has rotational symmetry. You rotate it twice to get it back where you start. And 360 divided by 2 is 180 degrees. 360 divided by 2 is 180 degrees. Okay. Number 23. Draw the image of the rectangle KEWL under a dilation with a center at A and a scale factor of 3, and record the coordinates of K prime, E prime, W prime, L prime. So this one is a little bit trickier because you can't just multiply the coordinates times 3 because we are not doing the center at the origin. We're doing the center at point A. So it's kind of like if we were to pretend that A was the origin and ignore these other axes. That's basically how we're doing this rotation. So I like to start with the point that's closest to the center of dilation, which is point L. I go out 1, 2, 3, and down 1 to get to L from point A. So I'm going to multiply those times 3. So instead of going out 1, 2, 3, I'm going to go out 1, 2, 3, 4, 5, 6, 7, 8, 9. And instead of going down 1, I'm going to go down 1, 2, 3. So from A, originally it was over 3 down 1. Now it's over 9 down 3 to take me to L prime. So L prime's coordinates are -1, positive 1, 2, 3, 4, 5, 6, 7. All right, so now I'm going to do K prime. So for K, as it is now, I count to the left 1, 2, 3, 4, 5, 6, down 1. So I'm going to multiply those times 3. So I'm going to go left 6 times 3, which is 18, down 1 times 3, which is 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, down 1, 2, 3. There's my point K prime. And that forms the top of my new dilated rectangle. Now I'm going to go to W. From A, I count down 1, 2, 3, 4, 5, left 1, 2, 3. 5 and 3. I'm going to multiply both of those dimensions by 3. So it'll be 15 and 9. So I'm going to go down from point A, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and left 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the point W prime, which forms the lower right vertex of my new dilated rectangle. Now, I can do the same thing with the E that I did with these other 3 points, or I can understand that all my angles are still going to be 90-degree angles, and this is still going to form the same shape of a rectangle, and just make point E be directly below K prime and directly to the left of W prime, and that will help me find point E. Oh, and I forgot to write down these other coordinates: K prime, E prime, W prime, L prime. So K ended up being at -1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. L was at -1, 7. Oh, we already got that one. W was at -1, -1, 2, 3, 4, 5. And E is at -10, -5. Now, if you connect these original point, make a line that goes through the new one and to the transform point, you will find that they all fall along a straight line. You will also find that if you measure the distance from the original point, if I could find sorry, my ruler markings are not very dark here. 1.5 times 3. The distances are going to be tripled. 2 times 3 is 6. So you can also do this just by taking the original and measuring how far apart is it from that center of dilation, and then drawing the line out further for a distance of 3 times as long. So that's another way to do this, especially if you're not working on the coordinate plane. It helps if you've got good, strong ruler markings to do that as well. There we go. All right. That is the end of our lesson for today. So I hope that you've had fun learning about dilations, and good luck with your assignment. If you need help, please let me know. I hope you have a wonderful day. Bye for now.